Hello everyone, welcome in the second lecture of Theory of Estimation. In this lecture, we will see examples on unbiasedness. The first example on unbiasedness is if x1, x2 digest up to xn is a random sample from Bernoulli distribution with parameter p, then number 1, find the unbiased estimator of P based on sample mean. Number 2 is show that T1 is equal to x1 into x2 is an unbiased estimator of P square. And number 3 is show that T2 is equal to x1 into 1 minus x2 is an unbiased estimator of P into Q. So we consider first answer of first term. We know that from the given condition expected value of xi is equal to p for all I, because the Bernoulli distribution, if parameter p is there, mean of each distribution is p. Then consider sample mean, that is x bar, which is equal to summation of xi upon n. So when you take a expectation of x bar, so expectation of summation of xi upon n. So we can take expectation inside, correct? So summation of expected value of xi upon n. But you know expected value of xi is p. Now how many times p is added? N times. So np divided by n. So your answer is p. So x bar is unbiased estimator of p. So second part, in the second part we have to show that T1 is equal to x1 into x2 is an unbiased estimator of p square. So expectation of T1, which is equal to expected value of x1 into x2, which is equal, x1 and x2 are independent because they are random. So we are taking random sample, so x1 and x2 are independent. So you can take expectation inside, expectation of x1 into expectation of x2. So this is equal to, expectation of x1 is p, expectation of x2 is also p. So your answer is p square. Number 3, we have to show that T2 is equal to x1 into 1 minus x2 is an unbiased estimator of p into q. So consider expected value of T2, which is equal to expectation of x1 into 1 minus x2, which is equal to expectation of x1 minus x1 into x2, so which is equal to expectation of x1 minus expectation of x1 into x2, which is equal to expectation of x1 is p minus, you can take expectation inside, so expectation of x1 into expectation of x2, so which is equal to p minus p into p, so which is equal to, if I take p common, what is remaining? 1 minus p, but 1 minus p is q, so p into q. So T2 is an unbiased estimator of p into q. Okay, example number 2 is, let theta and sigma square denote population mean and population variance respectively. Let x1, x2 dash up to xn be a random sample from this population. Then prove that t is equal to 1 upon n minus 1 summation xi minus x bar bracket square is an unbiased estimator of sigma square. So to prove this, consider expected value of t, which is equal to expectation of 1 upon n minus 1 summation xi minus x bar bracket square. 1 upon n minus 1 is constant, take outside the summation. Expectation of summation over I is going from 1 to n xi minus x bar bracket square. So first we square this bracket and then we take expectation inside. So 1 upon n minus 1 expectation of summation over I is going from 1 to n xi square minus 2 times xi into x bar plus x bar square. So a minus b bracket, similarly a minus b bracket square, a square minus twice ab plus b square, then which is equal to, if I take summation inside 1 upon n minus 1 expectation as it is, summation of xi square, correct, minus 2 x bar is constant, summation of xi plus n into x bar square, because x bar square is constant, which is equal to, so 1 upon n minus 1 expectation of summation of xi square as it is minus twice x bar is constant, and here if I divide this summation of xi by n, so I will get x bar, multiply and divide, so that term is n into x bar, correct, plus n into x bar square, which is equal to, so this term is twice n into x bar square and this plus n into x bar square, one terms gets cancelled. So what is remaining? 1 upon n minus 1 expectation of summation of xi square minus n into x bar square. So from this directly we can write the summation of xi minus x bar bracket square is summation of xi square minus n into x bar square. If you take expectation inside, what you will get? 1 upon n minus 1 expectation of summation of xi square minus n into expectation of x bar square, which is equal to, so you know variance of xi has the formula expectation of xi square minus expectation of xi whole bracket square. So which is variance of xi is, this implies variance of xi is sigma square, which is equal to expectation of xi square minus mean is theta, so theta square. So this implies your value of expectation of xi square is what? Sigma square plus theta square. Similarly, variance of x bar has the formula expectation of x bar square minus expectation of x bar whole bracket square. So this implies variance of x bar is sigma square upon n, which is equal to expectation of x bar square, and expectation of x bar is theta, so minus theta square. So this implies expectation of x bar square is equal to sigma square upon n plus theta square. So by putting these two values in this formula, we'll get the term 1 upon n minus 1 expectation of summation of xi square, that value is, so here expectation we take inside the summation of expectation of xi square, correct, minus n into expectation of x bar square. So this is the term. So 1 upon n minus 1. What is expectation of xi square? That is summation. I replace this by sigma square plus theta square. Minus n into, what is the expectation of x bar square? That is sigma square upon n plus theta square, which is equal to 1 upon n minus 1 n sigma square plus n theta square, addition of this constant term n times, minus n gets cancelled, sigma square minus n theta square, so which is equal to 1 upon n minus 1. This n theta square minus n plus gets cancelled. What is remaining? N sigma square minus sigma square, correct? So which is equal to, if I take sigma square common, what is remaining? N minus 1 upon n minus 1. So this n minus 1 gets cancelled. What is remaining? Sigma square. Therefore T is equal to 1 upon n minus 1 summation of xi minus x bar bracket square is an unbiased estimator of sigma square. Example number 2. Example number 3 is, let x1, x2 dash up to xn be a random sample from normal distribution with mean mu naught and variance sigma square. Let t is equal to summation over I is going from 1 to n mod of xi minus mu naught upon n. Then prove that t under root of pi by 2 is an unbiased estimator of sigma. So to prove this, first we consider expected value of t under root pi by 2. If the answer of this term is sigma, then we can say that t into under root pi by 2 is an unbiased estimator of sigma. So under root pi by 2 is constant. Expected value of t is summation over I is going from 1 to n mod of xi minus mu naught upon n. So we can take expectation inside. So under root pi by 2 as it is, summation over I is going from 1 to n, expectation of mod of xi minus mu naught upon n, which is equal. This is the mean deviation about mean of normal distribution. You know the formula for that, under root pi by 2 summation I is going from 1 to n, and this term is mean deviation about mean of this normal distribution, whole term divided by n. But you know, mean deviation about mean of normal distribution is under root 2 upon pi into sigma. So this is under root of pi by 2 as it is, and mean deviation about mean is sigma under root 2 upon pi, and this n as it is. And how many times this term, this summation? N times. So summation over I is going from 1 to n, which is equal to under root pi by 2 n sigma under root 2 upon pi whole term divided by n. So this n gets cancelled, root 2 upon pi gets cancelled. What is remaining? Only sigma. Therefore, T is an unbiased. Therefore, T into under root pi by 2 is an unbiased estimator for sigma. Example number 3. Example number 4 is a random variable x takes only two values 1 and 0 with probabilities theta and 1 minus theta respectively. Let x1 x2 dash up to xn are independent observations drawn from x, and we define t is equal to x1 plus x2 plus dash up to xn. Then we have to prove that t into n minus t upon n into n minus 1 is an unbiased estimator of theta into 1 minus theta. So consider the term expected value of t into n minus t. Okay. To prove this, consider term expectation of t into n minus t upon n into n minus 1. So which is equal to, we can take expectation inside, correct? So which is equal to n expected value of t minus expected value of t square divided by n into n minus 1. Only I take expectation inside and product. So when this is the Bernoulli distribution, correct? According to that, we can say that t follows binomial distribution with parameter n comma probability of success is theta, n comma theta. So expected value of t is, mean of binomial distribution is n theta, correct? And variance of t has the formula. Variance of t we know n pq, theta into 1 minus theta. So what we know, variance of t has the formula expected value of t square minus expectation of t whole bracket square. We are interested in expected value of t square. So expected value of t square is equal to, value of t square is equal to variance of t plus, if I take this term in this side, expected value of t is n theta. So you will get n square theta square. And what is the variance of t? That is n theta into 1 minus theta plus n square theta square. So if you take this term inside, you will get n theta minus n theta square plus n square theta square. So this is your expectation of t square, correct? So by putting these two values here, you'll get n into what is the expected value of t, that is n theta, minus what is the expected value of t square, n theta minus n theta square plus n square theta square, and whole term divided by n into n minus 1. So which is equal to n square theta minus n theta plus n theta square minus n square theta square divided by n into n minus 1, correct? Then n square theta and minus n square theta square term is there, correct? And second term is plus n theta square minus n theta. These two terms are there, and from divided by n into n minus 1. From the first term, if I take n square common, what is remaining? Theta minus theta square. From the second term, if I take minus n common, so what is remaining? Theta minus theta square, correct? If I take minus sign common, divided by n into n minus 1, which is equal to, so theta minus theta square is common, so theta minus theta square, what is remaining? N square minus n divided by n into n minus 1, so which is equal to, if I take theta common, what is remaining? 1 minus theta. If I take n common, what is remaining? N minus 1 divided by n into n minus 1. So n into n minus 1 gets cancelled. What is remaining? Theta into 1 minus theta. So therefore t into n minus t divided by n into n minus 1 is unbiased estimator for theta into 1 minus theta, correct? Example number 5 is, if x follows Poisson distribution with parameter m, then show that number 1 is x bar is unbiased estimator of m. Number 2 is x bar plus 2 is positively biased estimator of m. And number 3 is x bar minus 2 is negatively biased estimator of m. So to prove this, given that x follows Poisson distribution with parameter m, let x1 x2 dash up to xn be a random sample from Poisson distribution with parameter m. Then expected value of xi is equal to m for all I, correct? So if you consider expected value of x bar, which is equal to expectation of summation of xi upon n, which is equal to summation, we can take expectation inside, expectation of xi upon n. So expectation of xi is m, summation of m divided by n. How many times m is added? N times. So n m divided by n. So your answer is m. So x bar is unbiased estimator of m. First condition is satisfied. For the second, consider expected value of x bar plus 2. So which is equal to, we can take expectation inside, expected value of x bar plus 2. So which is equal to, expected value of x bar is m plus 2. And if you compare these two values, by comparison, expected value of x bar plus 2, if I remove these two, so this term is always greater than m. This implies x bar plus 2 is positively biased estimator of m. In the third condition, we consider expected value of x bar minus 2. So which is equal to expected value of x bar minus 2, which is equal to m minus 2. But if we remove this 2, then we will get expected value of x bar minus 2 is always less than m. This implies x bar minus 2 is negatively biased estimator of m. This is example number 5. Thank you.